Hello, everyone. I'm Greg Weaver. Welcome to the Audio Analyst. Pardon me. Today, I'll be sharing what will be the last conversation with Andrew Jones for now, though he has promised to do some others in the future, depending on some circumstances that will come up. But today's episode was all recorded during our first 3-hour session. Now, once you see it, I think you'll understand why it wasn't included in episode 41 as part of the more core KEF technology discussion. And while it does address some of the KEF tech and innovation, it's really more of an insight into the man and contains a lot more anecdotes, sidetracks, and diversions than any of the other episodes we've done. And honestly, in many ways, this one is my personal favorite, and I think you'll see why. I hope you enjoy it. Regardless of which one or ones you've enjoyed the most, I hope that this series of some 5.5 hours of conversation has enlightened you or in some manner shed some light on the depth of Andrew's capabilities and the extent of his efforts to consistently build great loudspeakers year in, year out, and with any manufacturer that he has chosen to work with. If nothing else, it should be clear that Andrew is one of the most innovative, enduring, successful, and respected loudspeaker designers in the industry, whose work has brought engaging and, for the most part, affordable music to an amazingly wide audience. Now, I simply cannot express how grateful I am to Andrew for his willingness to share so much of his time and insight with us here. With that, let's get into the final and most amusing conversation with Andrew. Hello again, everybody. Thanks for coming back. Again, we have the one and only Andrew Jones, who's been kind enough to spend some time talking with us. My fascination when I first got into this industry was I was a huge KEF fan. And so we're going to talk a little bit about KEF in this particular episode.
Yeah.
But let's go back to 83. You've just accepted the job there, and they're starting to they're putting you in research, and you're still geeking out, going, I work at KEF, I work at KEF, I work at KEF. Take it from there, sir.
Well, interestingly, one of the first projects I worked on, I mentioned that when I joined, when I interviewed, they just started working on the 1042 and the KM1 active monitor. So I joined shortly after, and the first sort of research task I had, they were working on using a new inductor core material for the inductors in the 1042. So traditionally it was either ferrite, which was not very good, or laminated steel cores, which were good but expensive. Well, there's this new material called iron dust or powdered dust cores. So it's an amalgam of powdered iron, bonded, heat fused together. Quite brittle, but it was supposed to have good saturation properties. But
was it kind of like a ceramic base?
It felt more like a ceramic, yes.
Yeah.
So you'd get a slug or slug with end caps that you'd bond onto it. And so my job was researching the saturation characteristics of that, looking at what point, depending on how many turns and what current level it would saturate at. So I was there putting pulses through and measuring that. So although I did not do any design work for the 1042, I felt at least there's a bit of my thinking in there in research.
There you go.
So I was put into research. Not surprisingly, I'd come from research.
Right.
KEF was big on research, and you've gone through some of the innovations, but the things, what interested me about KEF was it was not just maybe designing new drivers in a new cabinet. It was doing fundamental research and even into measurement techniques. And maybe not surprisingly, based on my earlier discussions, one of my first jobs was looking at measurement techniques and improving them. So KEF had pioneered the impulse measuring for a analyzer type approach. in the old days, if you had the ability, you had access to an anechoic chamber, and you did the old way of measuring. You do a sweep tone, and you track that the chart recorder, and that's the frequency response. But you need to be in an anechoic chamber in order to eliminate the reflections that come in from the room, because yes, to some degree, you want to know what a loudspeaker sounds like in a room, but that's always going to be different.
Yes.
The only constant is what the speaker itself does. And if you can know enough about what the speaker is doing, you can predict what it will do in a room.
In a room, yeah.
So you want to separate out all those variables. So you measure in an anechoic chamber. And anechoic chambers are very, very, very expensive.
And they're unnerving as hell the first time you've ever been in one. It's like you walk in and it's like, what the? I mean, because nothing, it's so abnormal. I mean,
yes.
I only did it once and it was like weird as hell.
I've spent half my life inside them. Probably accounts a lot for how I am now.
Did you not freak out the first time you walked into one?
The first time, yes.
Yeah, I mean,
I got used to it. And no matter how used to I am of being inside an anechoic chamber, when you crack open, it's normally double doors to get the full seal, because it's a room built inside a room. And the inside room is floating on vibration mount, so nothing can get in. So you crack open the first door, but as soon as you just slightly crack open the outer door and you hear the outside world, it's like this experience of depression lifts. It's just, the world, it's that deprivation of the sound. Even though I'm used to it, I'm not used to it, if you see what I mean. The contrast as you leave. So they're very expensive. So most companies didn't have access to that and worked with, trying to see what it does in a room. Now, KEF instead was pioneering impulse testing. So I mentioned earlier about Dick Heiser and the time delay spectrometry. So that's to say, if you sweep in the analog domain, the frequency domain, you can track a filter, and as long as the filter's moved on before the sound comes back from the reflections, is essentially rejected. The corollary to that in the time domain is gating.
Okay.
So if we put a short pulse, just a pulse like that, into a speaker, it contains all frequencies simultaneously with a certain known phase relationship between them. If you capture the response to that pulse from the speaker and do a Fourier transform, it gives you the frequency response of the speaker.
Okay.
So you put that pulse through the speaker, it went in perfect, it comes out with this tail and characteristics defined by its frequency response and its time domain behavior. Then after a certain while, that will get to the microphone. Later on, the sound that went off to that wall and came back arrives. So in principle, you start measuring, you continue measuring while that pulse arrives from the speaker. Then just before a reflection arrives, you go, I'm going to stop measuring.
Okay.
I have the anechoic response because I haven't allowed any reflections.
Any reflections, yeah.
Now, sort of true, but there's a flaw, a fly in the ointment. It needs the speaker to have stopped responding itself before that first reflection comes in. If you stop the measurement too short, you get what's called truncation error. And that means some of the signal was still wanting to be received, but you chopped it off. And that signal is primarily the low frequency response of the signal of the speaker. So if you chop it off, you get errors in the low frequencies.
Makes sense.
And so paradoxically, the only way to do a true impulse response is to measure in a really, really, really big room. Just like the only way to measure with an anechoic chamber accurately at low frequencies is in a really, really, really big anechoic chamber. And the only way in time delay spectrometry to do the same thing is in a really, really big room. So none of these techniques, they're all time delay spectrometry, sweep, anechoic sweep, and impulse response are all exactly equivalent in their requirements for measuring. The only difference with the impulse response is that you need a big room, but you don't have to treat it. An anechoic chamber has to be big, and also the bigger it is, the more wedges you have to store around. So the cost becomes huge. There's one we used to work with, and I'll get to it later.
Now, this couldn't be done outside because of ambient noises?
So if you try and do it outside, you got ambient noises, wind, weather, except in Southern California.
Well, but
and the other factor is you still got the ground. So although you've eliminated the other reflections, in order to eliminate the ground reflection, you got to put it up a large pole, and that pole has to be, if you want to go down reasonably low in frequency, it's got to be 30 foot high. And you got to get the speaker to the top of it.
And it's got to be stable and
stable, and so these limitations still apply. Nonetheless, KEF pioneered the use of that, and they were using Fourier analyzers built by Hewlett-Packard, and these are mainframes. So they're about that wide and 6 foot tall, and they have 32K of memory. Not meg, not gig.
No.
32K of the those little cores that are wound with wires going through them.
My first computer had 4K of memory.
Okay, and they the hard disk, the removable hard disk, was in a caddy. It was a 12-inch thing, and you inside a caddy to protect it, and then it would spin up, and then you could use it. So that all the system for doing the Fourier analysis was written in machine code to run on that 32K core memory, and we could do anything with that. We could do convolutions. They were 12-bit analog to digital converters, but we could record the music on there, and we could convolve the measured frequency response of the speaker with the music, so that we could take out the response of the speaker, and then when we played it back through that speaker, we're essentially listening to a perfect loudspeaker.
Wow.
This was in the mid-80s, and it started in the late 70s doing all this research. It was amazing what they did. And these Fourier analyzers cost an arm and a leg, and we ended up with about 4 or 5 of them. And so we used it for research, but also for production testing. So we had a purpose-built lab attached to what we call our impulse room. In order to get a long enough time delay, we had a 7 meter, so about 20. It was somewhere around 20 or 24 foot cube, and in the middle was a hydraulic pole, and we put the speaker on top and then lift it up to halfway in the room and facing upwards, and then dropping down from the ceiling we had a microphone, and you could kind of wind it down to set measurement distance, and that's where we would measure. The computer room, the air conditioned properly, the best room to be in always is the nicely air conditioned computer room. Not only did it have us engineers in there doing measurements, but it was also linked over to the production facility. So every speaker was 100% measured on the same Fourier analyzers under supervision of the engineers, because we were in the same room all the time.
Wow.
So any of the guys, they were on headphone link over to the production test chamber, which was a small anechoic chamber just for noise. And they would do the impulse testing. We could see every curve they were producing. And if there were ever any issues saying, oh, this response looks odd, show me. And we'd just go and have a look and, maybe this is going wrong. So we also use them for all the, in the production testing, we would sort and grade all the drive units. So the drivers get measured in one facility. They get sorted, everyone 100% measured. Then it goes through a computer program on those machines that establishes what the reference is, and then sorts them into sensitivity bands, half dB bands, and then gives them a code number or color. And then in production, we always take like numbers of
so
the mid-range
you're using
tweeter
matched drivers, basically,
and then match them all.
Yeah.
And then we had to sort out, well, how do we deal with if they're too far out? We either have to throw them out, but by mixing and matching, we could say, well, we can take all of the plus ones together, all of the plus halves, all the zero, etc. Or we might allow plus half in the base, zero in the middle, plus half in the tweeter, and the inverse. We'd have to decide what our limits are going to be to match them.
Sure.
But at the same time, all our crossover networks, we used to buy in, well, we wind all our own inductors. And the women were the coil inductor winders. And some of them even had machines at home, so they could wind them at home. But we'd wind all the inductors. We'd buy in capacitors at typically 10%, maybe to 20% tolerance. Measure every single one and sort them into 1% bands. Same with the resistors. Then these computers not only did measuring, but they did all the computer-aided crossover network design. And once you'd designed a network and got the frequency response that you wanted, you then went in and did a sensitivity analysis and looked at, if I changed each component in turn by so many percentage, what does it do with the frequency response? But you could then re-optimize the rest of the network, given that plus 5% component, and say, well, what do I have to change? Which tolerance band of those do I need in order to cancel the effect of the outer tolerance of that one? So that way we could get a much greater yield. So we sort them all into these 1% bands. Then we have these complex charts written onto the crossover network diagrams. And it said, if this is +4, take that as -3, and this is +1. And the job of the crossover assemblies was to go to the bins and just pull out all those different sorted components. So now we could buy them in at 10%, but get almost 100% yield and keep close tolerance of the networks. And we could even match those with the drivers.
Now, so that had to be way ahead of anybody else doing stuff like that. I mean, I've heard of other companies. I mean, that if you have a big enough budget, that's the right way to do it. Okay.
Yes.
But that had to be the first time anybody was going to that level to match components.
I'm sure it was. Because don't forget, at that time, there weren't programs available for doing crossover network design on computers. I just recently come from doing fundamental research in that. And so they'd got the system written on this machine, and that's the only reason we're able to do all that kind of thing. And so then I got into, that's all going on. I'm learning how to use those machines for research. And with 32K of core, you don't have graphical user interfaces. So every command for doing, even a command to say go, basically, was y space 0 space 0 space 20 space 0 space 20,000 space 1 space 1 space 0, something like that. And it meant perform this particular operation over this frequency range with phase and blah, blah, blah. And then another one similar to that to just plot the result. And you just learn all of these. And eventually I got really good at typing those. I couldn't type anything. If I had to then put into the header to describe the speaker, it was one finger at a time, which I still to this day do. But
well, just to interrupt here, I was programming computers in 1971. That's when I started to program. Hollerith punch cards, punch paper tape. So I understand the degree of instruction you had to use to get something to be done. So
I was a bit luckier than that at the university. So in '74, I was programming BASIC on DEC 10s and DEC 11s, but from a keyboard.
yeah.
Now my brother was doing Fortran on punch cards.
Well, we had both punch paper tape on a teletype and the Hollerith punch cards. But when I graduated high school in 1973, I could program in BASIC, PL1, Fortran, COBOL, machine languages, assembler. Not that it was of any use to me at that point. But I was one of the few. There were 4 of us in my high school that had a key to the computer room. My high school actually had a computer room, and there were 4 of us that had keys. So I went kind of geeky when I was young too, but a different way.
Yeah, no, that's amazing.
That's crazy. So, but yeah, at least you were doing something with it. I was just playing.
And so we started doing all this impulse testing. So that was established before I joined there, but then I had to learn how to use those machines. And then, I've always wanted to do more and more accurate measurements. And so, we were limited by the size of the space, even though it was a 7 or 8 meter cube, it still had its limitations.
That was the anechoic chamber, or just
no? This is what we call the
one room.
chamber. We had an anechoic chamber, but that was just a small one. The real place to measure accurately was the impulse chamber, and it's just a bare room, brick construction. It was scary sometimes working in there, because if the microphone jumped off its pulley, which was 24 foot up in the middle of the room, right? You had to get a ladder, not an A-frame ladder, but just a regular ladder, and there was an I-beam running across the middle of that ceiling, and you'd extend the ladder up and you'd lean the top of it against the I-beam, and you had to climb. Well, I always got that job. Climb up the ladder in the middle of nothing. It's not as if you're leaning up against the wall. You're in the middle of no space. And then you need both hands to kind of jiggle. So you'd lean your body against the ladder and you'd be going to get the thing back on. Not only was I the only one to do it, I was the only one who would do it, who everyone else was scared to do that. And then in one of the walls, so imagine a 24-foot square wall, right in the middle, because the building around it was 2-story. Right in the middle was a hole with a baffle in, and that's where we measured drivers. It was a 2 pi test facility. So a perfect infinite baffle 2 pi test measurement. And you accessed it from the second floor of the building on the other side of that wall. But I noticed I'd been measuring these drivers and I'd see this little blip, because when you see the impulse, you can see when every reflection comes in, and you see this little blip. And where's that coming from? It's not the wall, it's too soon. And so I examined the wall. I saw this small little electrical conduit that had been attached to the wall at one point to go to an electrical outlet. And it's only about that deep and that wide and attached to the wall. I'm thinking, and I make all the measurements, I think that's where this reflection is coming from. And so I went to Laurie, I said, I think this is where things are coming from, because I put a bigger object there and it makes it worse. I'd like it removed because I can see it in my measurements, this tiny little ripple. And he agreed, if you say it needs going, we'll get the electrician in and we'll move it. And we moved it, and sure enough, it went away. So it's good to have his trust on that one, because it was fascinating working with Laurie. He was so well-rounded, so inventive. We think of KEF as being founded by Raymond Cook, and he was a great guy, a polymath of the old school, great engineer. But all these innovations you're talking about were instigated by Laurie. And this is why we had to be members of the AES. We got to know everybody. And that was an important part. Because people ask me occasionally, well, I'm interested in speakers. Can I go to university to learn about speakers? I'm going, not really.
Not really. We had this discussion in our little thing the other night.
Yeah.
Yeah.
You go to university to learn the basics of physics and some acoustics and electronics and mechanical engineering, whatever it is. But basically, you don't learn how to design a speaker. You don't learn how to measure a speaker. You need to be mentored. You need to go to a company that is doing that kind of stuff.
Yeah.
And for me, that was it. And it's not just the engineers there. It was all the other engineers out in the area of hi-fi and research that, you know, world renowned, that we had access to. And so and all because of what Laurie had instigated. So it was an amazing opportunity to be there.
Well, how did he end up working there? Did he know Raymond Cook? Did he?
Yeah, I mean, he worked at Goodman's, you know, and it's just like over here. The hi-fi industry over there in England was incestuous, and you all move around. So
sure,
Laurie came from Goodman's. I think maybe Raymond was there for a while. I forget his complete history before he founded KEF. Yeah. But he brought Laurie along, you know, to be in charge of engineering while he was running the company.
Well, quite honestly, one of the best signs of a manager is picking the right people to work.
Oh, so that was exactly it. Well, Laurie was brilliant in himself, but he knew how to gather a group of people that could work well together and complement each other. And we had the best time. You know, it was always fascinating talking amongst ourselves about ideas, challenging or being challenged by Laurie. You know, that could be difficult because Laurie could be stubborn. He had every right to be. He was most likely right. My approach was always that if I go to discuss an idea with him and he's arguing against the idea, the probability is he's right because he's way more knowledgeable. But I'm the one who's just been doing this work to suggest it's something else. So maybe in this particular instance, I know more than he does, or my intuition is going to be more correct than his. Well, you argue to some point, and then you have to go, okay, let's agree to disagree. This is my course of action of what research I'm going to do to establish what is the actual reason or cause or result. And while I'm doing that, that gives Laurie time to rethink it also after that challenge, and maybe either come to a different conclusion himself, or as I start to feed back results, it allows him to rethink, and based on, you know, the observations that we're getting, rather than just I think. I remember at university, I'd gone to school with my best friend, both doing physics. He gave up after a few weeks and switched to social studies, which was philosophy, psychology, and sociology. Total difference.
A big change. That's a big change. Drastic.
And I remember a drunken discussion with him one night, and he was discussing something about philosophy, and I challenged it, and he said, no, you can't challenge that. That's a self-evident axiom. I go, what is a self-evident axiom? Well, it's an axiom. It's self-evident. that didn't get us any further, really. And so it's this idea that, where do we go from here? It's an impasse. How do you get out of an impasse? Well, you have to go and think and get results. So I would always do that. And some other engineers often would be amazed at how quickly I'd managed to get my way, but it's because I knew how to work with Laurie in that. So it was a fascinating time, and this idea of getting to know other people in the industry. Yeah, I've said about every month it was mandatory to go up to the Audio Engineering Society lecture.
Yeah.
And then after that, we would all go out to dinner together. So there'd be all the guys from Bowes and Wilkins, if Celestion, and especially all the companies down in that southeast area. Also, when Celestion would come down, Peter Walker from Quad, Peter Baxendale. If anyone was in town to give lectures, like Dick Heiser or Lipschitz and Van der Kooi, they would always get invited down to KEF first. They'd give us the lecture, we'd ask all our questions, then we'd drive them up to London for the lecture. That was going on all the time. And you mentioned about Celestion and the connection with KEF. So the research I was doing on computer-aided crossover design for my postgrad work, that was partially funded by Celestion. So I got to know Graham Bank at that time. Okay. And it was around those times he was developing the first SL6. He developed the copper tweeter, one of the first metal dome tweeters on the market, but very inefficient. So we go out to dinner and discuss all these different ideas without giving away company secrets.
Right.
But we'd ask each other questions and have fun. And especially if it was someone like Peter Walker or Peter Baxendale, because they weren't competitors.
Not really.
Quad was in the marketplace, but ASL 57 is not a competitor to all the KEF type of
to any dynamic driver. There's nothing. I mean, it's not. Yeah.
And Peter was such a wonderful guy, just one of the best ever. And if I ever posed a question over dinner, he'd think about it. Let me get back to you on that. And within a couple of days, I'd get a phone call. Hey, Andrew, Peter here. I was thinking about what you said over dinner the other night. And he'd lay out this beautiful explanation. And it would never involve complex maths because, like both he and Peter Baxendale would say, if you need complex maths to explain it, you don't even fully understand it yourself.
I can see the kernel of truth to that, but still, yeah.
So had a fantastic time with him, and even after I left and came to the US, whenever I went home, I'd go and visit him and drink whiskey with him through the evening, talking about ideas. I remember one time we've been discussing this idea. Peter, I have to go because I've got to get home because I've got to fly back tomorrow. I said, why don't you email me with your thoughts on it? I don't do email. He's in his 70s or something like that at that point. And so I said, okay, write me a letter. I don't really write letters. What do you mean you don't really write letters? My handwriting is so bad that nobody can read it. I said, well, we don't really have any other options here, do we? So send me a letter. So airmail comes a couple of weeks later, and it's from Peter. And I open it up, and oh my God, the handwriting was so bad. It was so bad. And I'm trying to read it. And it's only because I knew the context of what we discussed that I was able to make headway.
Piece it together.
Yeah. But I came to this one line, and I couldn't work this one out. And I showed it to my wife, my friends, all my doctors, took it to my local pharmacy because they have to read prescriptions scrolled by physicians. Nobody got it. And it took a good 2 weeks of keep looking at it. And I then worked out what it said. It says, I apologize for the handwriting. I told you it was atrocious. And that was the most atrociously written.
That's pretty funny. That the hardest thing to translate was his apology about his writing. That's hysterical.
Yeah.
Now you talked about some very important people. You worked at some point. I know you talked about Siegfried Linkwitz, who I never met, but I had a few exchanges with him electronically. You were talking about you talked about Thiel and Small, Richard. You talked about working with those guys.
Yes. So this is the thing. People would come and visit KEF.
Yeah.
So Siegfried, whenever he was over, he would come because he would stay with Laurie. Laurie got this huge house out in the Kent countryside, and he and his wife would come over and visit, and then Siegfried would come into KEF and we'd all get together and chat ideas. And whenever he was researching anything, if you look at some of his early published work, like for example on the Linkwitz-Riley crossover, he was using drivers we'd supplied to him for free for doing all of that. So we got to know him well then. Neville, Thiel and Dick Small, Thiel Small Parameters. We always used to meet up with those guys, and to the extent that Dick came to work on sabbatical. So he got a year's sabbatical from the university in Australia, and he came to KEF to work that sabbatical. So that was the first long exposure I had.
Yeah.
And since I was in research, and obviously he's a research guy, we worked closely together. But I remember, although I hadn't met him, on and off, he's now coming to work for KEF. And so I got in early that morning. And the Gary Larson cartoons?
Yes.
The Far Side? So I'd recently, on one of my trips to America, been introduced to Gary Larson, and I'd got one of his books, and the cartoons were so funny. But I remembered this particular one. So Dick Small, Dr. Richard Small,
yes,
originally worked at HP in America, then moved to Australia. That's where he did his research and got his degree. And he's a nerd. He's a typical, and working for HP, they had pocket protectors with pens in and all this kind of stuff. He was like that, button-down collar shirt, the nerdy glasses, everything. And coming from Australia recently. So for the first morning that he's going to turn up to work at KEF, I'd found a cartoon in one of the books. And it is all these kangaroos standing around in a field. And in the kangaroo's pouch was a pocket protector. With pens in it. All of them wearing round nerdy glasses.
Oh, God.
And it was titled Kangaroo Nerds. And I thought, perfect. Photocopied it, put it on his desk. Then I got kind of worried because I knew he must be in, but I heard nothing. I'm thinking, crap.
Was he offended? Was he?
What's his sense of humor like? I don't know. I've had a long humorous session with him because it's Dr. Richard Small. He's famous. And after about an hour later, the door flies open to the lab, and in walks Dick, clutching this piece of paper, shouting, "Who put this on my desk?" And I'm like, "Oh, no." And me, sir. And he burst out laughing. He said, "That's one of the funniest things I've ever seen."
And you're like, that's good. That's funny.
So sometime later, we had a visit from a young transducer engineer for a company, oddly enough, called ELAC. No connection with German ELAC.
Okay.
But it was a OEM supplier for car speakers. And we were involved in some kind of car project, so we were working with these people. So they sent this young engineer. So at one point he comes into the lab and asking me about teal small parameters. And I said, you know, I'm not kind of thoroughly familiar to just give you all the answers, because we don't use teal small parameters. They are an approximation. They're a good way of getting to a quick answer, but they're not fully accurate. And we don't use that because we do complete modeling of the equivalent circuits of the speakers to do all of this. But you know what? I'll tell you who can answer.
It's right around the corner.
Dr. Small is up in the front office. And the guy looks at me and what do you mean he's in the front office? I said, well, he works with us. Yeah. And the guy goes, I didn't know he's still alive. He's so famous, I thought he must be dead. That's why I'm trying to get as famous as I can before I die. You know, it's no good being famous after you've died. So I said, let me go and introduce you to him. So I take him up to the front office. I walk into the office and I shout out, hey, Dick, this guy here thinks you're dead. Perhaps you can put him right on this. The guy turned fuchsia. He was so embarrassed.
Oh, God.
So,
that's
yeah,
hysterical.
and then Lipschitz and Van der Kooi. You know, if you want to, so Professor Lipschitz, Stanley Lipschitz.
Stanley, yeah.
So professor of, I might get this the wrong way round. One of them was professor of mathematics, and the other was professor of physics and into hi-fi. So if you had any fundamental stuff that you needed answering, like what is the mathematics of eddy current losses in the pole piece, they would write a paper on that. They would research and write a paper, or the real directivity of a finite line source, and all this kind of stuff. And they publish papers, and you just ask them questions. And ultimately, Van der Kooi's son, Jeff, came to work with us on sabbatical. So it's this constant revolving door of people coming in that we had access to. And ultimately, what brought me over here, Floyd Toole, long-time friend of Laurie's, and he was the instrument that brought me over here.
Well, I read a lot of his work on psychoacoustics, and it was game-changing for me because I'm not an engineer at all. I've got a bit of an engineering background, strong mathematics background, but reading that stuff about psychoacoustics, it was like, holy crap. This is to me, I thought it was breakthrough stuff for me. The things that he dealt with and the way it affects everything else, it was different for me. I've never met him, I've never spoken with him, never emailed him, but I've still got a bunch of his papers out here that I look up every once in a while because I think it's fascinating stuff. Now, did he come to KEF too, or did you just?
Oh, yes. Whenever he could. Became longtime friends with Laurie, both he and his wife, and Laurie and his wife. And especially of interest, we did this huge project that was a cooperation between, when I say we, I mean KEF, and the University of Copenhagen, or the Technical University of Denmark, which was in Copenhagen, and Bang & Olufsen. The EEC had got these research projects called Eureka. If it was collaboration between a university and industry, you could get a grant for a proposal to do research work. So we all got together and proposed this idea for studying room acoustics, the influence of the room and speaker directivity on the sound that you hear in a room. So the Technical University got one of Europe's largest anechoic chambers. It was just huge. It was at least from top to bottom 30 foot high. I know because we put all the equipment on top and I had to climb up there every day on steps to keep connecting up and servicing it. And so the work was, we at KEF began by modeling the acoustics of a room. So we built this program by the image ray analysis. Imagine that every surface is a mirror, and you put a speaker in there, and you can see the reflection of the mirror of the speaker in that mirror, in that mirror, in that mirror, all the way around you. You see a speaker, then you see the reflection of a speaker. Just like these parallel infinite mirrors, you get infinite reflection. We built a program on the computer to calculate where every image and image of image and image of image of image would be. And we could insert in that program a speaker of any directional characteristic and walls of any absorption characteristic, and calculate what the room response would be.
Wow.
But more importantly, what you could see is you could group, a lot of these images would clump together. So we could determine through a subset, if we put speakers in an anechoic chamber, spread all the way around us, it was on a 3-meter radius. So a 20-foot sphere of speakers all the way around you and below you. We had, I think, 30 of them. And we built a discrete, because again, there was no DSP chips in those days.
Right.
30-channel DSP engine that, based on the data from the computer, could calculate the frequency, the signal that would be coming at you from that speaker direction based on the nearest clump of reflections. And then ultimately some artificial reverberation, because you couldn't calculate enough tails to make it truly believable to begin with. So my job was building the speakers. They were concentric drivers, and we mentioned Uni-Q earlier on.
Yeah.
As we were developing the concept of Uni-Q, we decided to use them for this project. So before we did anything manufactured for production, I was hand building concentric drivers, 5-inch drivers, 1-inch tweeter, in a spherical enclosure, driven by a current output amplifier designed by Peter Baxendale, with EQ that I designed to make a flat response. And these were all driven, they were bi-amplified, initially driven by Bang & Olufsen Penta amplifiers. So 60 of those on the roof, down to 30 sets of speakers. So my job was all building and maintaining all these speakers. One of our other guys physically built a 30-channel DSP rack, and we set that all up in the chamber. And so you could go in there and listen to a pair of speakers and then turn the room on. So the feeling that you said you got when you listen in an anechoic chamber, because of the lack of sound and the lack of reflections, you initially experience that. Then at a flick of a switch, you're in a room. And then at a flick of a switch, sort of, you can change the dimensions of the room or the absorption in the room. You can turn the floor off.
Wow.
So you can listen to what the effect of the floor bounce is, or turn the ceiling off. So ourselves in the university did all that structure, and Bang & Olufsen, well, actually, Bang & Olufsen and ourselves did the structure of that, and started running experiments. But the guy from the university, Søren Beck, his job was to do all the psychoacoustic testing. And so our part of the project was finished. We weren't psychoacoustic or the kind of the mathematical analysis you have to do when you're doing that kind of listening tests. He was. So he then used that facility to continue to research ideas on directivity and room acoustics. He then ended up working for Bang & Olufsen. So I'm convinced that, that latest weird looking speaker that they did.
All the facets.
All of that work that was instigated back in the early 90s that we did between ourselves. And, to what degree, I know Floyd certainly was not involved as such, but he experienced it because he knew what we were doing. I don't know whether he'd ever talked to Laurie about things we should be trying, or which way the communications went. But certainly, Floyd ran with that concept and built a mini version for doing the research he did while he was still at NRC, and then continued all that psychoacoustic work over at Harman, because he had already moved to Harman, and as KEF was changing hands again, and ultimately joining with Celestian and whatever, Laurie left because he was invited to come to Harman by Floyd, and then a year later I joined him there, all because of Floyd. Funny story. It's a shame you've never personally met Floyd, because this would be even funnier. But so I'm walking around Cedia, I think, on time, and I got with me this young woman from China who was one of the suppliers. This was while I was at Pioneer. She was a supplier of drive units to Pioneer. And so I said, well, if you're going to the show, I'll take you around and introduce you to all the speaker people I know, see if you can help them out, get some business for you. But so we're walking around and we bump into Floyd. And I said, hey, Floyd, how are you doing? I'm good. Said, let me introduce you. This is Louisa. She's from one of our driver suppliers in China. And I say, Louisa, this is Floyd Toole. Do you know who Floyd Toole is? And she said, no, I don't. And so I said, well, Floyd is an industry icon. And Floyd kind of does this. Oh, I don't know about that. And quick as a flash, I go, okay, Floyd, I'll drop the I.
Okay.
And he goes, ouch, that hurt.
Oh, God. Oh, man. You brought up the Uni-Q thing. I've always wondered, I mean, when looking back at it, it's like, what an obvious idea. I mean, it just makes sense. But it wasn't initially. I mean, when you look at it, it's like, that makes sense. Both drivers, 1 point. I mean, but do you know, like, where the original idea came from, or what it makes sense now.
I was still in research at that point. Mike Goff was the chief engineer for systems, and Lloyd started talking about this idea. And if you look back on it, it's not in one respect. I'm not doing it down in this sense. It was sort of not obvious because people weren't doing it.
Right.
But then it was also sort of obvious why you'd want to do it. And it wasn't the first time sort of something like that had been done. Tannoy dual concentric.
Right.
It's the principle of what you're trying to achieve is identical. You don't want separated drivers. You want them coaxial to begin with. You want the directivity control that the cone gives, and the extra loading on the tweeter at the lower frequencies to aid efficiency. Time alignment, if you can. That's not such a big thing, and certainly the tannoy didn't align them because the tweeter is behind the magnet system, so it's very much delayed. In a conventional speaker, the tweeter is ahead of the woofer. In the tannoy, it was behind the woofer. But those existed. What was different was that Laurie had started to hear about magnet technology. It was at the time that neodymium was being developed.
It just came out, yeah. It was just
came out.
Yeah.
And in the past, even if you'd wanted to do a concentric driver, it wasn't really possible, other than doing it the way Tannoy had done, because you couldn't shrink a tweeter.
Couldn't make the motor small enough, yeah.
To put it now, experimentally, before we got the neodymium, they did it with an Alnico magnet, because
Really?
ferrite has to be flat and large diameter to get the right working point for the magnetic flux. Alnico has to be the other way. It's long and small diameter. So they specially constructed a drive-in with a very long voice coil former, so they could slip an Alnico magnet down there. And it wasn't very strong, but it gave them the ability to experiment and see what this thing could do. But with the idea that, well, as neodymium becomes available, we can replace that with a neodymium slug. But neodymium wasn't available for speaker manufacturers. It was being developed for electric motors. So there didn't exist a magnet in the form factor that we needed. So we had to specially tool something.
Okay.
And at that time, it's extremely costly to tool a neodymium magnet. And yet we needed a 1-inch diameter slug about, 1/8 of an inch, 1/4 of an inch thick. So that was, I forget how much, tens of thousands of dollars to tool at that time. And so we know we were the first to do that because it didn't exist before we got the tool. And
well, there were some problems with the original Uni-Q, weren't there? I mean,
yes. So this gets into a whole different territory in that. So technically, we got it working, and we'd measure it, and we'd go about designing it in our normal way. So we could do all the measurements, measure all the off-axis responses, and certainly there was a problem in the 10 to 15K region, because as the sound travels up the edge of the cone and hits the disruption of the surround, it will cause a reflection and re-radiate from there and cause an interference dip over a reasonable range of angles. And at that time, there's nothing we could do about that. You need the surround on the
right.
woofer. Whether it's going out or in, it's still
one way or the other. I mean, it's got to move. Yeah.
So, but the first obstacle we had was in designing the frequency response that we wanted, and indeed listening to it in our KEF listening room. It sounded pretty good. And because of the cost of tooling up for this, we decided we can't afford to just put it as a reference series speaker, limited production, because we need to recover the tooling costs.
Right, yeah.
So it actually, unusually for a new technology, got introduced in an affordable speaker. However, as soon as people started listening to it, and especially in big live rooms in the States, it sounds like this. And that's because we'd misunderstood the requirements for balance between on-axis and off-axis.
Off-axis, yeah.
It was much more directional through the treble range than all other speakers. Well, all other two-way speakers.
Right.
And as a result, the sound in a room was unbalanced. The sound in the KEF room was quite dead. And ultimately, we ended up rebuilding that room to make it more representative, because we're making some wrong judgments. It was almost too anechoic. Yeah. And so it got out into the marketplace, and people didn't like the sound balance. And sometime not long after, I ended up as chief engineer, and so I started doing a lot of work on improving Uni-Q. And one of those things was both how do we deal with the dip in response, the diffraction dip, but the other were, and shape of the cone to get the best directivity response, because the cones at that point were very deep. But the other factor was sound balance. We don't want it flat on axis. And it ties in nicely with the work we were doing at the university, with being able to decide on what is an optimum directivity response of a speaker, what is an optimum room treatment. The fact of, well, as the speaker becomes more directional or not uniformly directional over all frequencies, how do you balance between on-axis sound and reflected sound, because the ear makes some judgment based on both of those.
Sure. Yeah.
And so as you change the ratio between those two, depending on what you do to the room or what you do to the speaker directivity, you change what you hear, and it changes from room to room. So it was clear that we'd made it too flat on axis at the expense of the off axis and the reverberation response in the room. So ever after, when I was designing Uni-Qs, I'd always make it pretty much, I'd design for flat at 15 degrees off and allow it to have a gentle up tilt on axis. And that went a long way to fixing.
That helped balance it out, right? I mean, that, so it was less reactive in rooms than it would have been.
Yeah, and then because of that, you look, well, that ratio between on and off axis will change whether it's an 8-inch driver, a 6-inch, a 4-inch, because the cone depth is changing. And so you have to be aware of all of that.
Sure.
And the listening informs the design by measurement. You know, we get into this whole thing, which Floyd, this circle of confusion, he calls it, in a different area, which is you're listening to something to judge something, but you don't know what that original thing was supposed to sound like. So how can you judge anything? There's that in the listening, but also why do we know that we want a flat response from something? At some point, we had to do listening tests and determine. Yeah, I mean, maybe that's too trivial, because surely a replay chain should be flat, right?
Well,
but beyond that, degrees of flatness and audibility of bumps in response in different frequency ranges, and in this particular, the bounce between on and off axis sound, what should that balance be? Listening tests are needed for that.
Sure.
Listening to something, and I won't yet get into, well, listening to what, you know, I just mentioned. But you got to listen and say, well, which measurement represents what I want to hear?
Yeah.
Because a speaker is three-dimensional. You know, a piece of electronics, of course it should measure flat. Oh, look, I measured it, it's flat. Of course the speaker should be flat. Oh, look, I measured it, it's sort of flat here, but it's not flat off there, and it's not flat up there, and it's not flat, and it's not flat in the room. Which flat? Which flat matters? Which ratio between the curves matters? That's a much more difficult psychoacoustic study.
Yeah.
And remains one of the most difficult parts of speaker design. And interestingly, Raymond Cook, he came down to me one day and he said, "Hey, Andrew, I've been looking through some of my old stuff and I've copied something for you." It was from a I swear it was 1934.
Oh my God.
It sounds as though it ought to be 54, but I haven't found it yet. But again, it's buried in my boxes somewhere. But I think it was 1934, GE Research. And it was a curve, a frequency plot showing frequency and sectioned into bands, and said, if this level is high, horns will sound bright.
Oh, wow.
If this section is, say, too low, voices will sound. And there was the sibilance region, and there was the warmth region, going all that
time. From the 30s?
The 30s. And
wow.
They were the exact same observations you'd make on any speaker system to this day.
That's pretty amazing.
Yeah. So,
and he had just run across them and saved them and decided to share them with you? Or is, I mean,
yeah.
wow.
Hang down, Andrew. I thought you might find this interesting.
Wow.
Yeah.
That's crazy. Now, you have to be proud of the time you spent at KEF, because, like I said, you know, I was just a novice out there in the world selling this stuff and loving music, going, look at all the crap they're doing over. I mean, these guys are, you know, you guys were pushing the limits every day. It seemed like through the 80s into the 90s.
Yeah.
Is there anything that you contributed to or were part of there that you think was particularly useful or beneficial to the average listener today? I mean, that changed how speakers came out of not just Europe, but how speakers in general are seen today?
I think first, as I mentioned, understanding how to measure a speaker. You know, if you're going to do any judgment on during a design process, you need to know how to make accurate measurements.
Sure.
And so many people don't. We developed, the idea of doing, because we knew Don Keel, the idea of doing near field measurements, in-box measurements, all those kind of things to get better accurate low frequencies. We'd started working with Peter Baxendale on the idea that I said, if the impulse goes on too long and you truncate it, it creates low frequency errors. So can we force the impulse to be shorter? What is a short impulse?
Oh.
If we extend the speaker down to DC, isn't that perfect? So it should be infinitely short. And we found that the more we extend the speaker and try and measure the impulse, it got worse. Okay, what about if we make it shorter? So we determined that a speaker that is a second order 200 hertz will decay fully to allow you to truncate within 10 milliseconds, let's say.
Okay.
So can we force the speaker to be a 200 hertz speaker, then truncate it, then undo the forcing function? So we built this box that we'd measure near field of the speaker, determine what its sort of low frequency response is. Then we put a filter in that starts rolling it off at 200 hertz. Then when it gets down to where the speaker itself would naturally roll off, we stop rolling off. So now we've turned it into a perfect second order high pass at 200 hertz with a shorter than 10 millisecond truncation. So we can truncate it, then divide back through that forcing function. We've now got the response of the speaker. So we built these boxes under instruction from Peter Baxendale to do this. So that became part of our armory when measuring. So the idea of measuring accurately, and I've continued to develop that in all instances, is the first thing. And that was started by KEF.
Yeah.
And in fact, that was you mentioned about the KEF cube. That was what started development of the KEF cube. This idea of being able to put a filter in that knows exactly what the low frequency response of the speaker does and change it to something else. So we thought, well, instead of cutting it off at 200 hertz, why don't we make it go down to a lower frequency? And so we could take the 1042 or other speakers that we purposely designed in combination with the cube and have a module that is designed to exactly counter the low frequency roll off. So basically a matched equalizer.
Okay.
We would now, the original, the 1072 was the first time we did this. And the 1072, I designed and built all those cubes. And you've got dials on the front, and you could just dial 50 hertz cutoff, 40, 30, 20, and just change the cutoff frequency in that speaker. And besides extending the amplitude response down lower, the phase response is where the phase response starts to rise. That's moved down to a lower frequency. So it's more accurate phase response down to a lower frequency.
Oh.
And it was interesting listening to 107 and just switching this knob and hearing how it changed your impression of the music. And it wasn't just about bass. You'd be listening to a soprano in a hall, and as you extended the bass response, it just became more believable because you heard more of the natural reverberation, the low frequency reverberation of the hall, and it became more real.
Yeah.
So that's an instance where research begat directly a product. The 1072 was my first reference series speaker as having become chief engineer.
Chief engineer.
From product, from research into product. Because Mike Goff, who was chief engineer, he went off and worked for BMW. How could he?
Andrew, thanks for this, man. This has been a blast. I was so lucky to be part of this industry in that era and be, granted, I was just a retail salesman. I moved up into management and, teaching other people how to sell, but I got to play with all this stuff. So, it would come out and we'd read the white papers, which weren't, what we got were just like marketing papers, but it gave us a good story to tell on the floor. And it was so easy to sell KEF speakers back then. Yeah. Well, if people wanted to spend that kind of money, you guys were just doing so much great stuff. It was such a hotbed of innovation, and dude, you were a huge part of that. You were there for all of that stuff.
Yeah.
And I want to end up quickly here, but when did you end up becoming the chief engineer? When did that happen?
It would have been early, late 80s, maybe 90s, something like that. I
and you stayed there through about 94?
94.
Like that? Okay. Yes. And it's just so much fun to go back through that stuff. I can't tell you how much fun it's been.
Okay. Thanks, guys.
Damn, that was fun. I hope you enjoyed this considerably more personal glimpse into the man who has been such a driving force and innovator in the field of loudspeaker design for coming up on 5 decades, as much as I did. His work is not only appreciated by music lovers, reviewers, and journalists, but he also enjoys the respect and admiration of other industry-leading loudspeaker designers and manufacturers, some of whom build products that sell for over 3,000 times as much as Andrew's least expensive products. One last consideration before closing out this series with Andrew. Once this pandemic is behind us, if you ever have the opportunity to experience Andrew presenting at a show, don't pass it up. Make sure you find time to stop by and listen to him holding court. You'll be as impressed by what he has to say about the products, the stories he shares, and what you get to hear. Thank you for all the support. If you find merit or value in the information I'm sharing here, please subscribe. Don't forget to like and to share links to your favorite episodes with your friends and on social media. And be sure to leave your comments and questions for me. You may support the channel using Patreon, Venmo, or PayPal, or even by securing display advertising at the Audio Analyst website. And links for all options are provided in today's description section. As always, thank you for taking the time to drop by and visit today. Please stay safe and keep the music playing. Till next week, cheers.